Hey everybody, in this next video lesson, I'm going to talk about how real gases behave compared to the ideal gas. I first want to talk about the ideal gas law. We all know it as PV equals nRT. But if you take the P times V, that equals a number, and you take N times R times T, and that equals a number, those two numbers would be identical to each other. So basically what you can do is divide nRT onto this side, so you have PV over nRT, and that's going to equal 1. This is called a compression factor. For the ideal gas, the compression factor is 1 and is always 1, no matter what the conditions. But real gases can shift above or below this number. I want you to take a look at this graph down here. We've got a dotted line that just kind of goes all along 1. That's the compression factor, PV over nRT, for the ideal gas. But these three lines, the teal, the brown, and the purple, all take a look at how real gases behave when the pressure changes. As you can see, we're looking at pressures that are 300 or 600 or 900 times atmospheric pressure. So as the pressure increases, the gases behave less ideally, and we're going to talk about why they go down and then they go up, and why they're not all like the ideal gas. But it's worth noting that real gases do act ideally at normal environmental conditions. At 1 atmosphere pressure and at 293 Kelvin, real gases behave pretty much like the ideal gas. But what happens if we push them past these ideal conditions? Now, things that will play a factor are pressure, the intermolecular attractions, the volume and mass of the gas, and even the temperature. And we're going to look at all 4 of these here today. We all know that the ideal gas has 0 intermolecular attractions, but real gases do not follow that same rule. Real gases, although have little intermolecular forces attracting to each other, they do have some. So let's compare real gases versus ideal gases. If you have 2 samples of gas that are the same volume, and one is the real gas and the other is the ideal gas, well, the ideal gas would come in at a line that's right about here. We'll call this whatever. We'll call it 1 atmosphere. Well, the real gas, because there is very, very little intermolecular attractions, but there is some, will be slightly less than 1. The difference here is because the intermolecular attractions make the real gas behave as though there's slightly less pressure in that sample. If the pressure for the ideal gas is 1 atmosphere, the pressure for the real gas would be slightly less than that due to the increased intermolecular attractions. Now, when do you think this would matter the most? In other words, when would this observation have the largest effect? Well, let's say, for example, you take a gas and you compress it into a very, very small volume, which means the pressure goes up, 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 up. Well, those gases are going to be bumping into each other more often because they're compacted into a tighter volume, and those interactions are going to be more frequent. And if there's intermolecular forces playing a role, well then the real gas will attract other real gas particles more, and as a result, the real gas will have a lower pressure than the ideal gas. This would also come into play if the gas's temperature is really, really low. When temperature is low, the gases aren't moving quite as fast. And if the gases aren't moving quite as fast, when they bump into each other, those intermolecular forces, although weakly shown by real gases, would play a role. They would have an effect on the real gases, and the real gas would feel like it's less pressure because those particles are traveling much slower. Ideal gases wouldn't matter because they don't have intermolecular forces, so their pressure would maintain, but at colder temperatures, a real gas would have slightly less pressure. Now, what about the particle's volume? The actual gases, the particles themselves, take up a little bit of space. And so we believe that the ideal gas, each atom or molecule has no volume of its own, but real gases do have a very, very, very small amount of volume. So if this dotted line represents the volume of the ideal gas, well, because each of the particles of the real gas do have volume, well, then the actual volume of the real gas would be slightly larger than the volume of the ideal gas, because in a real gas, the particles add to the volume of the gas itself. And as it says here, in any scenario where the volume of the atom plays a role, we see that real gases act less ideally. So it begs the question, when would this have the biggest effect? Well, once again, let's consider a high pressure environment where the volume has been decreased to a very, very small amount, and so the pressure increases. And when all of those particles are packed in so tightly into one space, then their volume begins to matter. If the gases are spread out and the particles barely recognize each other exist, well, then the actual volume of the particles doesn't matter. But when you compact it real short into a very small space, then the volume is very, very small and the pressure is high. And so at very, very small volume or high pressure environments, the actual volume of the particles begins to have an effect on the pressure of the gas. And at those low volume, high pressure situations, because the real gas has actual volume, it will appear that it has increased in pressure compared to the ideal gas. So let's talk about a situation where pressure is high. Once again, pay close attention that the ideal gas is at exactly 1. This is what's once again known as the compression factor. Now, one thing to notice about the ideal gas is that if it never changes its compression factor when the pressure increases, then it could never compress into a liquid. But we know that this is true of real gases. If we increase the pressure of a real gas, we could make it turn into a liquid, such as like liquid propane, those tanks that you use for grilling, or even liquid carbon dioxide can be pressurized and turn into liquid carbon dioxide, and then it can be used as those keyboard cleaners that you would use to clean out the dust and stuff inside your keyboards. So ideal gases would never become liquids under high pressure situations. But because intermolecular forces matter in real gases, when you begin to increase the pressure, as you can see along the horizontal axis, the molecules, the gases, begin to act less ideally. And this initial drop on some of these gases, as you can see, CO2 drops, and so does CH4, and even N2 gas drops as you increase the pressure. This initial drop is due to the increased molecular attractions between these molecules. These substances have higher IMF, and so they begin to drop or behave less ideally compared to the ideal gas. Now, eventually, they turn back up, and that is the point at which the volumes of the particles begin to matter. When you get to a pressure that's about 200 times the atmospheric pressure for carbon dioxide, the volume of the particles begin to behave like the volume is increasing, as we talked about in the last slide. Increasing IMF makes a gas feel like there's less volume, but when factoring in the volume of the particles, the gas starts to behave like there's more volume. And so eventually, as you compress tighter and tighter and tighter, the gas begins to go back up. So the downward is due to increased intermolecular forces, and the upward is due to the increased awareness of the volume of the particles starting to matter. The big thing that you need to take home is this, that anytime you have stronger intermolecular forces or bigger atoms, a real gas will act less like the ideal gas. One more thing before we leave this slide I want you to notice is that the heavier the gases are, the stronger the intermolecular forces, and the stronger the intermolecular forces means the deeper the dive in this initial stage. CO2 is the most polar of all these gases, followed by CH4, and followed by N2. And the two least polar gases happen to have very little drop initially because they are essentially nonpolar and have no intermolecular forces that are attracted to each other. And because of that, these particles don't have that initial drop. Hydrogen gas and helium gas don't notice initial drop. They just start to begin to increase because their volumes start to matter. The awareness of the particles of the gases start to show an increase in volume compared to the ideal gas. And that's why these don't have an initial drop. So in this case, mass matters because as mass increases, intermolecular forces increases, which is why you see this initial drop when the volume decreases. Lighter gases behave more ideally. Now what's happening at low temperatures? Well, as the temperature gets really, really low, as in we're approaching absolute zero, the particles begin to move slower and slower, and what this means is that they have less energy to bypass the very, very, very weak intermolecular forces that exist. At normal temperatures, it's warm enough for these intermolecular forces to basically be a non-factor, but at lower temperatures, we have less energy, and so those intermolecular forces begin to make a difference. Heavier atoms are affected more because they are already moving slower. So in other words, if it has an increased mass, it's already moving slower, and so their intermolecular forces begin to matter even sooner. But gases with stronger intermolecular forces are also affected more because their inherent IMF is already stronger. Take a look at this. This is the same gas at 3 different temperatures. At really low temperatures, the gas takes a big dip and then increases, but as you warm it up, the dip is less, and the increase is less. And at really, really warm temperatures, this gas behaves very similar to the ideal gas because it's closest to that horizontal line. Basically, what I'm saying is anytime real gases move slower, they act less like the ideal gas. So let's apply what we just learned about to a couple of real gases. First one, why does helium follow the ideal path the best? Remember, the ideal path is a perfectly horizontal line. As the pressure increases, helium shows very little change compared to the ideal gas. Well, first of all, it's a very small particle. And a very small particle is only one atom and has a mass of 4 grams per mole. So essentially, it has very, very little intermolecular forces. And because it doesn't have very high intermolecular forces, you don't see it attract other particles of itself, and so it behaves most ideally. If it had stronger intermolecular forces, like the ammonium does, then you would see it begin to drop initially, because remember, this initial drop is due to increased intermolecular forces as the volume decreases. But because helium doesn't have any, or very strong intermolecular forces, I should say, then you don't see that initial drop. Now let's discuss ammonia in greater detail. First, let's take a look at what the molecule ammonia really looks like. It's a trigonal pyramidal molecule with a pair of electrons on the nitrogen. And that pair of electrons acts as a partial negative charge, which means this area down here is the partial positive charge. So it is a very polar molecule. And as we talked about, polar molecules are affected in this initial drop. The volume is perceived to be less at this point than it really is because of that increase in molecular forces. But once you get to about 300 atmospheres of pressure, it begins to turn up. Because at this point, once again, the volume of the particles starts to matter, and if you compress those gases into a tighter space, the actual volume of the gas particles make it appear the volume is higher than it really is, which is why you see this turn up over at 300 atmospheres of pressure. And finally, let's talk about nitrogen. Why does it spike, this red one, why does it spike as the pressure goes up? Well, of these three gases, nitrogen is the largest mass. It's nitrogen plus nitrogen, which is 28, which is the largest mass of these three. And when you have a large mass, it's assumed that you have a large volume. And larger volume particles show this perceived increase in volume as the pressure increases because the volume of the particles matter more. So although nitrogen gas is a nonpolar molecule and it doesn't have very strong IMFs, which is evident due to the fact that it doesn't drop initially, it stays pretty flat. But as the pressure increases, it begins to spike because the volume of the particles begins to make the gas feel like there's more volume than there really is. So let's land the plane here and answer these two questions. When does the ideal gas law become less valid? The ideal gas law becomes less valid as the pressure increases, and it also becomes less valid as the temperature decreases. Under high pressure conditions, those intermolecular forces can begin to act on the other particles in a real gas, making the volume seem to drop compared to what the real volume is. Also, at those high pressure environments, the volume of the real gas begins to become a factor, where for the ideal gas, the volume of the gas particles are not a factor. And as the temperature decreases, those intermolecular forces also begin to play a role because no longer are the particles traveling fast enough to break the intermolecular forces. The intermolecular forces attract each other, and we witness a drop in perceived pressure. Finally, what type of particles act less ideally? One type of particle that doesn't act ideally are particles that are polar. Remember, polar molecules have increased intermolecular forces, and if those intermolecular forces are acting on the particles, then they behave less ideally. The stronger the polarity, the less ideal the particle. Also, the mass of the particles matters. Larger mass particles have assumed larger volume, and the larger volume particles in a real gas make the pressure perceived to be higher than it really is. Well, that takes care of this video lesson. Thanks for watching.